everybody, and welcome back to Pre-Algebra. Today we're going to be on Lesson 80. We're going to be talking about scientific notation. So if you would, please turn your books to page 186, and go ahead and get out your notebooks, and we're going to start our bell ringer. So I'm going to give you guys 1 minute to do these 3 problems on a sheet of paper, and then I'll be calling on you guys randomly to answer these, and then we'll move on to our lesson for today. Okay? So I'm going to give you 1 minute starting now. When you finish, if you will, just put your pencil down so I know you're finished. Everybody's finished already? Okay, awesome. All right, guys. So real quick, Lucy, can you give us the answer to number 1? What is 10 to the 3rd power equal? 1,000. That's correct. Good job. All right, Thomas, can you give us number 2? What is 10 to the negative 2 power equal? 0.1. Almost. Really close. Scott, could you help us out a little bit? What is 10 to the negative 2nd power equal? Correct. 0.01. Good job. Good job. Or 0.01, right? All right. Well, Scott, while I have you there, we go ahead and do number 3 for us real quick. 10 to the negative 4th power equals, correct, 0.0001 or 0.001. Good job. All right. Great job, guys. All right. So we're going to move on to our lesson for today, and we're going to talk about scientific notation. So what is scientific notation? Why do we use it? And when are we going to use it in the real world? So those are all great questions. So first of all, let's talk about what it is. So scientific notation is a way of writing numbers, a different way of writing numbers, to where we can write really large or really small numbers in a compact, smaller way that makes it easier for us to understand. So here's an example of a number that's written in scientific notation. So you have the first part. This part is called the coefficient. And this number will always be less than 10, but it will be greater than or equal to 1. So in other words, it will never be smaller than 1, and it will always be smaller than 10. So it will always be between 1 and 10. Another way to think about that is that the decimal will always be behind one number that is not a 0, right? Or in other words, the decimal will always go behind the first non-zero digit, followed by this multiplication sign. So when we write numbers in scientific notation, we're writing the number saying that it is this number multiplied by, or in other words, the product of this number and 10 to some power, or as we call that, our exponent. We call 10 the base. And the reason why we do it this way is because all of our numbers in our number system that we use is a base 10 system. In other words, the first 10 numbers, if you count 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That equals 10 digits. So you count 0, 0 to 9 is 10 digits, and then after that 10 digits, then we have to add a new digit, right? So in other words, after we get past 9, then we have to start with a second digit, right? So after 9, we get 10, so we start with a second digit. So this is called a base 10 system. That means after the first 10 digits, you have to add a new digit. So what is the purpose of all of this? Well, scientific notation is incredibly important. As you go through high school, you're going to use scientific notation in all of your science classes at some point. Biology, chemistry, all of these types of classes. And then when you move into college, you'll use it even more in those higher level chemistry and biology classes and physics and so And again, the reason why we use this in so many of these different fields, especially when we get into things like engineering and astrophysics, and we look at things on the astronomical scale with planets and stars and things of that nature, or we're looking at the atomic level or subatomic level of things, and we're looking at really tiny things. We need a way to be able to quantify those things, and a way to be able to do arithmetic with those really large or really small numbers in a way that allows us to be able to maintain accuracy. And so, let's look at some real world examples of where we use these. So one area that I mentioned a moment ago that you're going to see this used a lot in is in astronomy. Because in astronomy, we're talking about really big objects out in space, or distances between objects that are very, very far away. In astronomy, of course, we measure the size of planets, the size of stars, the distance between planets and stars, the distance between our solar system and different galaxies, and all of these different things, the distance between different galaxies and stars, and so many things, and these are very large distances. And this is one of my absolute favorite lessons to teach, because it always reminds me of, in the Word of God, in the book of Isaiah and the book of Job, it talks about how God made the heavens and He stretched them out. And in the book of Isaiah, it talks about the entire universe will fit between the span of God's hand. That the span in Old English was the distance between the thumb and the pinky. So the entire universe fits between the thumb and pinky of God's hand. Isn't that amazing? But yet, according to modern science, that distance is billions of light years. In other words, it's so far away that it would take billions of years for light to travel from here to here. From God's pinky to God's thumb. It would take billions of years for light, as fast as it travels, to get there. And just to give you some perspective, the light from the sun can reach the earth in 8 minutes, and the sun is millions of miles away from the earth. In 8 minutes it can make travel that distance. But yet at the same time, God also knows the very small things. See, Jesus said that God even knows the very number of hairs on the head of every person that's ever lived. So God knows things all the way from the largest of things down to the very small, because God is omniscient, right? He knows all things. And scientific notation reminds me of that, right? It reminds me of the magnitude of God's creation, from the very small subatomic particles all the way to the distance of the entire universe. It's pretty amazing when you think about it. Now, as human beings, we can't possibly comprehend all of these really large and really small numbers, but scientific notation helps us to have a way of breaking that down so that we can understand it better. So let's look into scientific notation. Let's look at an example. So again, this is the same example from earlier. And again, this first part is called the coefficient. And then it is a number that is, again, less than 10, but bigger than 1, or greater than or equal to 1, that is being multiplied by 10 to some power. Now, if you remember back to our bell work that we did, the exponent can also be negative, right? So it can be positive or negative. And so we're going to talk a little bit more about what these numbers look like if they have a positive exponent, what they look like if they have a negative exponent, and how we write these correctly. So I'm going to write some examples and some non-examples of numbers written in scientific notation. So here's examples on the left, and some non-examples on the right. And I want you guys to tell me the difference. So if I had 4.5 times 10 to the positive third, that's an example of a number written in scientific notation. And we're going to talk about what that number equals here in just a minute in standard notation. An example might be 3.7 times 10 to the negative 2 power. Now let's look at some non-examples. We're going to talk about why these are non-examples. What if we had 42.5 times 10 to the negative third power? What's wrong with this number? Why is that not scientific notation? What do you think? Thomas? Well, so you say a negative exponent is the problem, right? Does everybody agree with that? Right, exactly. So we have one over here that has a negative exponent, and it's okay, right? So that's a good thought, Thomas. So one of you guys, what do you think? What makes this a non-example then? So the negative exponent's not a problem. What is the problem? Right. That decimal is not behind the first non-zero number, right? There's two digits here. We always have to make sure that that decimal is over here, right? So if we were going to write this correctly, we would actually write this as 4.25 times 10 to the negative second. And I'm going to explain how I did that in a moment. But for now, just want you to understand that this would be the correct way to write that in scientific notation. Okay? Let's look at one more non-example. What if I just wrote the number 325? Why is that not in scientific notation? Scott? Right, there's no multiple of 10. Right? What else would we need to do with this number? Yeah, you'd have to move the decimal, wouldn't you? You'd have to have that decimal behind the 3. So this would be 3.25 times 10 to the second power. Right. And I'm going to show you guys how I'm getting these numbers here in just a moment. So we're going to do some examples here. So we're going to learn how to convert numbers to and from scientific notation and decimal notation. So if you look at this table on our right here, we have all of these numbers. So we have 4,500. And in scientific notation, we write that as 4.5 times 10 to the third, right? Something to think about, 10 to the third. What is that? What does that equal? 10 to the third power. We did this earlier. Right, 1,000. So it's just 4.5 times 1,000. So we get 4,500, right? And then if we have 450, that's 4.5 times 10 to the second power now, right? And to the first power would be 45. 10 times 0, 10 to the 0 power, what does that equal? Right, 10 to the 0 is 1. So 4.5 times 1 is itself, right? It's 4.5. And then when we start getting into numbers that are lower than 1, that are less than 1, then we start seeing negative exponents, right? 0.45 is 10 to the negative 1, and so forth. So what I want you to think about is there's always an invisible decimal at the very end of every number, right? And so if we're taking a number in decimal form, which is just ordinary numbers that we're used to, and we're trying to convert that to scientific notation, we need to start with our invisible decimal. And then we have to count how many times we're going to move that digit until we get to move that decimal until we get behind the very first digit. So how many times did I move that? Scott? Yeah, 3. So we get 4.5 times 10 to the third, right? This number, think about it two different ways. There's two different ways you can think about this, right? 4,500 is a big number. It's bigger than 1, so we're going to get a positive exponent. And we get 3 because that's how many places we move the decimal, right? But if we was to go down here, we need to move that decimal until we get behind the first non-zero number again, right? And so we get 4.5. How many places do we move the decimal this time? 2, yeah. And since this number is smaller than 1, or another way to think about it is if we were going from scientific notation to decimal form, we would move the decimal back 2 places. To the left, we get a negative 2 exponent. Right? Good job, guys. All right, we are almost out of time for class today. So I want you guys to write these on your marker boards real quick. I want you to convert these to scientific notation, and then here in just about a minute, we will share our answers and we'll talk about it. And then we'll call it a day, okay? Wow, that was fast. You guys already have your boards up? Okay, awesome. Lucy, that's correct. 250,000 is 2.5 times 10 to the fifth power, or you would move the decimal 5 places to get over behind the 2, right? Scott, I see that you have the correct answer for number 2. Good job. 7.1 times 10 to the negative 4th power. Good job, guys. Well, that's the bell, so I hope you guys have a wonderful rest of your day, and we'll see you tomorrow. God bless.